So I think this is going to be the shortest video, even though it might be one of the most complicated pieces in our weak strong titration combination. I'm going to be walking through a weak acid strong base combination, and noticing here this is a weak acid strong base titration, but there's also the weak base strong acid titration. Philosophy is sort of the same in terms of how you calculate and do problems, calculations with that. So this is just sort of like the background and the theory, highlighting, our last video was on the strong combination. Now we're going to be doing and thinking about these weak strong combinations. What's unique with both of them is prior to the equivalence point, you will be in a buffer region. So what does that mean you can do for your calculations? Henderson-Hasselbalch equation. Okay, after the equivalence point, you cannot use the Henderson-Hasselbalch equation. Okay, but before the equivalence point, you can. Weak acid strong base titrations will have equivalence points that are greater than 7. The way to remember that is with a weak strong combination, the strong piece determines what the pH is going to be at after the equivalence point. If the strong part is the base, you're going to be pH greater than 7. If the strong part is the acid, like we have here, your pH at the equivalence point will be less than 7. So those are some qualitative questions that you might see, just thinking about that. And then there's the quantitative piece of actually calculating what the pH is. All right, so I'm going to go through this a little bit more quickly because we already sort of dealt with the anatomy of a titration curve, if you will, in our last video. So I'm going to walk through briefly these 4 points and how you think about doing the calculations at each one. So before the titration begins, you basically are going to have, in this case, a weak acid solution. So we haven't added any hydroxide, no chemistry has happened, so the only thing that's there is a weak acid solution. So the pH is again dependent on the H3O plus concentration, but with a weak acid, we have to think about an ice table to determine just how much H3O plus that makes. So this becomes like a learning unit 6 problem. Hey, I've got a weak acid solution. What's the pH of it? Okay, you'll notice here that we start a little bit higher than we did when we had a strong acid. The pH isn't as low. All right, before the equivalence point, let's say we've added 20 milliliters of our sodium hydroxide. We're halfway to our equivalence point. What's happened now, because we've got a weak acid here that's reacting with our strong base, what's happening is that we are we're getting rid of some of that weak acid. We're actually generating the weak base. We've got, or I should say it's conjugate base, so we've got weak acid generating the conjugate base. We've got a buffer solution. So what's happening as we go through this middle region here is we're getting rid of some of this weak acid. We're generating some of the conjugate base, and when we have a weak acid and its conjugate base in solution, we've got a buffer. So we've got a mix of HA and A minus before the equivalence point. That means we've got a buffer, which is really great because we can use the Henderson-Hasselbalch equation to calculate the pH. Okay, so the pH is going to be dependent on whatever that ratio is. We're going to have a slight increase in pH because some of our acid army is sort of being converted into our base army, but we can use the Henderson-Hasselbalch equation to figure out that pH. All right, when we are at the equivalence point, we already said that if we've got a weak acid strong base titration, the equivalence point is going to be greater than a pH of 7, but here's how you go about calculating exactly what it is. So remember, at the equivalence point, we've added 40 milliliters of our hydroxide. That's reacted with all of the 40 milliliters of our HA. So all of our HA has been neutralized by our OH minus. If we look at our little picture here, the only thing that we have in solution, there's water in solution, there's sodium cations in solution. The only thing that we have in solution is the conjugate base. Okay, so this all of a sudden becomes like a salt problem. We've got the conjugate base in solution. So what's going to happen is we need to consider that equilibrium. Now we can't use the Henderson-Hasselbalch equation at this point. We're going to need to use an ice table to figure out what the pH is. Okay, after the equivalence point, now anything that's happening is we're just adding additional hydroxide to solution. There's no more army to react with anymore. So all that we're going to be doing is increasing the OH minus concentration, and then this becomes just like a problem we had with the strong. The pH after the equivalence point is only dependent on the excess titrant that's added. There's no more chemistry that's really happening once we've gone past that point. All right, so problem solving strategy, I'm going to go through these slides kind of quickly because they're the exact same slides we had in our strong. We need to know what we're doing. Who is in solution? Strong, weak, what's going on? This again is the weak acid strong base, so that's going to dictate the kinds of things we need to think about. We still want to be able to orient ourselves by figuring out the volume to the equivalence point. Okay, sometimes it'll be easy to do in your head. Maybe you have to do a calculation and then figure out, orient yourself. Are you before the equivalence point? I have a buffer. At the equivalence point, I got to do an ice table there. After the equivalence point, well, then I'm pretty much just considering the excess titrant that I've added. Okay, we're going to go through those calculations in an extra video. Same strategy is going to help you reconcile what's going on here. Think about who's in solution. What's the chemistry, and then after the dust settles, the equilibria that can happen. We always use ICF tables for chemical reactions and ICE tables for chemical equilibria. Making sure that we match equilibrium constants for the chemistry that's happening, and then knowing that we're solving for the right species. If we're solving for pH, we need to be thinking about H3O plus concentration. All right, so a weak acid strong base calculation. The extra problem that's online, the extra credit Edpuzzle video, has to do with thinking about titrating 40 milliliters of a 0.1 molar propanoic acid solution with 0.1 molar, here's our strong base, sodium hydroxide. Okay, 4 different calculations: before you begin, before the equivalence point, at the equivalence point, after the equivalence point. Before you begin, we've got a weak acid, so we need to use an ice table and a Ka value to think about what's going on there. If it's before the equivalence point, we can use our beautiful Henderson-Hasselbalch equation, but we need to make sure that we adjust for the fact that the volume has changed, so that's going to change our concentrations of species. So that's how this problem becomes a little bit more difficult. At the equivalence point, we basically then need to be thinking about the conjugate base that's there. So we need to just flip over and start using the Kb equation. And then we're going to be generating hydroxide in solution so we can get POH, which then we can convert via our around-the-block calculations to pH. After the equivalence point, we're going to use an ICF table to figure out kind of who's there after the dust has settled. And then we're just going to consider the excess hydroxide. That excess hydroxide is going to be what drives our change in pH. All right, so extra credit video is going to run through how to do all of these calculations, but this was the theory on a weak acid strong base calculation. I'd encourage you to take a look at the strong acid weak base calculation. Now, this is starting with the weak base in our beaker, which is why we start up at a high pH, and as we add in acid, our pH is going to go down. Notice some similarities here. Before the equivalence point, we always have a buffer. At the equivalence point, the only thing in this case that we're going to have in solution is the conjugate acid of our weak base. And then after the equivalence point, the only thing that's going to contribute to changes in pH is the excess strong acid that's been added. All right, that's our strong-weak titration combinations.